Hi, today I'm going to present our work HalluciDet, Hallucinating RGB Modality for Person Detection through Privileged Information. Object detection is the task of locating objects on image. You receive as an input the image, and you have as an output the class labels and the bounding box of the detected objects on this image. The RGB and IR modalities can contain complementary information that can be used to improve the object detection. Normally, the IR images are used during low light conditions, while the RGB images are more used during daylight conditions. Some of the related works try to adapt the RGB detector for infrared modality using or fine-tuning or traditional image-to-image transformations with the detector frozen, or for example they try to use learning strategy where they can try to translate from the IR modality to an RGB modality that's going to be better for the RGB detector. To summarize, previous non-learning methods demonstrate that we could have an intermediate image representation generated by an IR image better adapted for the RGB model. Also, previous learning methods focus on image-to-image translation rather than the final detection task. These methods are not optimal for object detection or introduce artifacts on the image due to the adversarial mechanism that can hurt the detection performance. To tackle these problems, we designed the HalluciDet. The HalluciDet is composed by the hallucination laws that is going to guide the knowledge from the RGB detector that is frozen and distill this knowledge to train the hallucination network that is responsible for the image-to-image translation. So, the hallucination loss is composed by the detection part and the regression part, and we use this to distill the knowledge of the RGB detector. We compare our method with different strategies, ranging from non-learning strategy and also learning strategy. Some of the non-learning strategies are, for example, the histogram equalization, histogram stretching, blur, and inverting the pixels of the image. And also some learning strategies are the UNet, cyclogram, cut, and fast cut methods. We compare our method for different detectors, for example, the FCOS, RetinaNet, and faster RCNN on the LLV IP dataset, and our method shows better performance than the methods compared for different detectors. We also compare our method with different adaptation strategies, for example, with fine-tuning and also the no-adaptation, and we had better performance for the FLIR ADAS dataset. Also, we try to stress as much as possible our method, trying to reduce the number of parameters and see the impact on the performance. We can see a good trend where if we had more resource, we can introduce more parameters on the hallucination network, then we gain some performance on our method. We also try to train the method with different number of trained samples, and for the LLVIP dataset with around 20% of the trained samples we are close to the fine-tuning, while for the FLIR ADAS dataset with around 50% of trained samples we are close to the fine-tuning. Some of the qualitative results shows that our method has less false positives than the others compared for the different datasets, and we also have a more precise detection. Here we can see a comparison between our method and the performance of the detector on the RGB modality. To conclude, we propose the HalluciDet method, a new approach that leverages the privileged information from the pre-trained detectors in the RGB modality to guide the end-to-end image translation for IR modality. It is guided by the proposed hallucination loss function incorporating a standard objective detection terms. It relies on the straightforward yet powerful image translation network to reduce the domain gap between the IR and RGB modality, guided by the hallucination loss. If you want to know more about our work, you can access our code on GitHub or our paper. Thank you.